Hello everyone, and welcome to my very first video on this channel, the Open Source Wizard. Yeah, we'll be talking about all the types of cool open source physics, coding, and yeah, just math related to how our universe might work, and honestly, the magic inside of it. I've tried to record this multiple times, and it has not gone well. I'm not good at script recording, so I'm just gonna treat it like I'm talking to a friend and go through the bullet points of what's going on. Recently, I had a really interesting breakthrough in one of these topics, specifically space-time, because I've loved physics since I was a kid. And I thought it was definitely worth trying to share it, even though I don't like being on camera, so you might not see me all the time. But anyway, quick disclaimer before we get into the actual video and the content. Yeah, this project is currently not peer-reviewed, so treat this like a thought experiment and less of a fully rounded out, established idea. And take your own spin on it. We are the peers trying to review this right now, so have fun and yeah, enjoy. We're going to break this up into about 7 main topics, foundational concepts, antimatter versus matter, the many-world interpretation, and Big Bang and redshifting, as well as light cones, Planck steps, caveats, and future works that I plan to be working on and hope to have more people who are interested in collaborating with and chat about. We'll end off with the general conclusion and what's happening next. I really hope you guys enjoy. I'll try to make this as interesting as possible and put diagrams where I can. And yeah, sit down, grab some popcorn, and we're in for a long haul. No, we're not. Okay, next. Foundational concepts. Treating time as a radial dimension. What does that mean? Why would we want to treat time like a radial dimension? Well, in standard physics, we talk about time as like a straight line, the present, the past, and the future. And even in like sci-fi movies, like when they travel backwards in time, they still experience their time moving forwards, right? Like it's still forward motion in time. We never really experience time going backwards. Another thing is time from physics should be treated as a spatial dimension, completely indifferent from the x, y, or z coordinate. The only like small tiny caveat, shout out special relativity, is we put a time c for the speed of causality or the speed of light. And for those who might not be familiar with it, it's kind of the idea that the speed of light is the speed limit to the universe and also the speed limit to the propagation of causally affected events. Yeah, so you can almost treat that as one unit of time as one TC. Cool. Yeah, we have this idea of time as a straight line of the past, future, and present. But if we replace that line with a circle that expands outwards in all directions, at least starting with a 180 to 0 degree, we get a really interesting visualization that comes out of it. So let's set the scene a little bit and set our little experiment space. We have this one-dimensional universe, and we have this particle that lives in this one-dimensional universe, and he's just going back and forth, bouncing around or moving left and moving right? But we don't really know where the particle is at any exact given moment in time. There's this uncertainty principle that makes it hard to know exactly where the particle is moving, which direction it's going, or which specific position it is without losing more information. It's like a blur effect. There's also some other interesting things about this world, like time dilation and spatial contraction if the particle moves fast enough, you know? And yeah. So how does treating time like a radius help in this scenario? Well, we can picture it like the particle is choosing to go into one of these specific positions, and we want to measure which outcome it has. I'll go more into this a bit later. We have this expanding circumference of options, right? This particle is at one specific moment in time, and we don't know if it's going to go left or go right, but those are the only options it has. It's a one-dimensional universe. So we can assume it goes both ways in like a superposition of sorts. And let's say we're measuring this in Planck time that's relative to TC, that unit of space I was talking about before. So then that means that the first tick, we know the particle's kind of somewhere in the center. The second tick, we're not sure if the particle decided to go left or go right. So let's say it decided to go both ways for now. It's in a superposition. And then in the next tick, well, the only options the particle has is it could either go back to the center or back outwards again in the next like interval tick. So you can kind of see how after each tick, the position where the particle is, or the certainty in like its next future location, starts to become a lot blurrier, because it's like, oh, did it go backwards? Did it go forwards? Is it all the way to the left now? Is it all the way to the right? Yeah, all these options, right? You can see this as a list of finite options, like a finite set of options. So it's not infinitely like it's everywhere all at once, but more that, oh, it's either here, there, or some other well-known position after this tick of time. And you can treat that like a continuous spectrum. Like in our world, a 2D or 3D world, we don't have just left or right, we have left, right, and forward, which gives us this kind of radius of options, right? All these options are equally possible for us to choose. So let's assume that the particle goes in all those options at the same time. And the particle just measures itself in the actual position it ended up going to. Almost like this particle is a projection of the actual possible states it could be in at that moment. We're getting a little hypothetical, but let's go back to this idea of a finite radius. And then as time grows, that finite radius of options grows with time. Almost as if time is a radius to the circumference of the circle of probable positions to find that particle at time tc scaled by Planck lengths. And the reason why we want to divide it by Planck units is because there's this idea that between a Planck unit step, the particle could be assumed to be in a superposition of both its options, right? So how does it go from a superposition of both its options to a collapsed version? I know, right? Doesn't make any sense. So instead of assuming that it collapsed, we assume that it just measures the position it chose to be in. And now we have this radius of places it evenly and equally could have been at that position moment in time, measured by a radial length. And we can say that these are different worlds that live on top of each other in a sense, in some hyperdimensional way. Like that the particle didn't just move to the left, it moved to a universe where the particle moved to the left. A little meta, but it really helps, and it does some wonders when it comes to special relativity. Yeah, so that's what I mean when I say treat time like a radius that grows outwards. And as this radius grows outwards, the circumference is growing infinitely larger and larger, but it's still a structured shape of a circular circumference. We're choosing 180 to 0 for math purposes, but you can also imagine 360, because we can, move in 360 degrees in our universe. But our particle is one-dimensional, so it's only going left and right, or maybe back to its original center position. And as time grows, the radius grows for this. Cool. So we have an expanding circumference and a radius of time. The circumference is like a ripple almost in this water of sorts, right? And as that moment starts from initial state, it ripples outwards to the next possible states. And the present is kind of like the wavefront or the crest of that ripple at that exact moment in time that we're looking at or experiencing. The future hasn't happened yet, but we can also see what possible directions we're able to move into, or what possible futures we may be able to measure our experiences in. Interesting, right? And as time grows, all the infinite possibilities grow with it. But we're still stuck in this world line or light cone of possibilities. Get more into that later. So this idea can merge neatly with other principles, specifically the Minkowski metric, and we can use special relativity. If you think of time as a radial part, you can start picturing events like ripples, but mainly the Minkowski metric. So right now we're just using like CT just because we want to treat time like a spatial dimension. You can almost think of it like Newtonian physics, because it really is like still very much Newtonian physics. But if we want to move into special relativity, that radial line of time now becomes the Minkowski metric, a radial line of space-time. and it simply grows relative to the formula of the Minkowski metric, which still ends up being relative to TC, assuming that the particle space doesn't move. And as we start to move into this world of a radius and a circumference of probability and a radius of time, it helps to start using a new coordinate system, which I'm sure you might be familiar with. Spatial coordinates. Yeah. Yeah. Oh, what's this, 10th grade math? It's coming in clutch. Let's go. Spatial coordinates. So you have spatial coordinates, right? And what is a spatial coordinates? Well, it's a radius defined by some length, and then an angle which defines the position that you can find it. So let's say we have a point over here. Well, then the radius would be some length of 2 units, just cuz, or I'll use this line right here, 2 units, just cuz. And then the angle is some units, or x degrees, right? So we can find out our position and our moment in time by a radius length, moment in time, and our position, an angle in space. This is simplifying it, because in space-time, space and time is the same thing. So this unit is really space and time as it propagates outwards, and that angle is space and time as we curve through our motion in space-time into specific worlds, multiverses of probable states we could measure that may be occurring simultaneously or parallel to one of each other. It's like almost sector slices of the universe. Interesting concept, very interesting concept. But like, what's the benefit of seeing the world like this? Like, what do we gain from this view? The big thing that made me see it this way is because there seems to be a lot of symmetries in physics, or like two sides of the same coin. You think of mass and velocity, or space and time, and some other thing. The electronic field and the magnetic field, they seem very analogous to one of each other. So it kind of hints at this idea that, as Einstein stated, shout out OG, that E equals mc squared plus pc squared, or like pc squared, mc squared plus pc squared, right? And that really says that energy is both momentum plus mass together. Like, that's all we are. It's just energy in the form of momentum and mass. And if that is the case, then mass and velocity is the same side, two opposite sides of the same coin, energy. And space and time, again, is two opposite sides of the same coin, energy. And especially in the space-time way, you see, while we seem very still in space-time, we're actually moving at the speed of light when we're perfectly still through time. Like, we're moving, the ticks of the clock of time as it progresses are happening as fast as they could happen at the speed of c. But when we move, we divert some of that energy that we're using and convert it into motion energy. Almost like we're running on this ripple, like this wave front. Like, you can picture a surfer that's like just riding the wave forward, but then he's like, let me move. And then that physically causes him to take energy from the space and curve his direction. And you see this curve-like motion. That curve-like motion in the spherical plane is analogous to time dilation in spatial contraction. Because while time is ticking normal for the person going still, because they chose to move, their time is now relatively slower, but they still experience time in radial direction that is still like normal, right? Cool. There's a bit more on the idea of these symmetries, and it leads into the idea of matter and antimatter. Because what we've done here by taking this one-dimensional world and then plotting out where the particle may possibly be over time is really like taking a wave function and doing a transformation into spatial coordinates. And what you see is these probabilities or amplitudes that mark its probability density of these wave function of a wave function, where it's like, what's the probability of seeing the particle on the left or seeing the particle on the right at time x? And you'll see some value that relates to its probability. We've made a probability space. But when it comes to matter and antimatter, how do we handle these things? A good way to think of it is matter and antimatter are the same thing, mass, but with different amplitudes, and CPT reversed. Now, a little quick disclosure on CPT time reversal. CPT time reversal talks about charge, parity, and time getting reversed. So I like to picture it as a 180-degree sphere, right? You can also picture it as a 90-degree light cone. And then I like to do this. Boom. That right there, you see that? Boom. Yeah, I know. That CPT time reversal right there. Did you normal time? CPT time reversal. Boom. See how it crosses and then everything flips in direction, parity, and charge as well. And I'll go into charge and time because it's moving backwards in time and then its motion is now reversed, or the physical behaviors of properties now reversed. A big thing about this is like, or a simplified way of thinking about it is like time, antimatter is matter just moving backwards in time. And it's a weird concept. Like, how is matter moving backwards in time? And how does that make it antimatter? And is there antimatter right now moving backwards in our time and space? Or what's going on here, Chef? I'll tell you more. All right, so antimatter and matter in our universe is more matter. So there isn't just random antimatter moving back in time, but we will go into it. There is antimatter existing in this universe, per se. You can imagine a 180 to 360 degree side of this probability space where there is more antimatter just moving backwards in a symmetrical way to the matter moving forwards. I'm not sure if it has to be perfectly symmetrical. This is, once again, not peer reviewed. But yeah, so that's the concept where you have matter and antimatter in this time reverse space. And at first I was like, it's a cool symmetrical thing you can do, a little CPT, cross finger thing, but does it relate to any math? Well, during this like research phase, I'd worked with the Klein-Gordon equation first, and then moved on to the Dirac equation, which handles spin and also describes the wave function behavior of antimatter components of matter. And when I plotted it out using the same like idea, I got a much more detailed plot compared to the Klein-Gordon, where I'd literally just flipped the wave function moving forward in time, backwards in time, but it still showed the exact same behavior. And that level of symmetry with the Klein-Gordon and the Dirac, while also showing extra detail of how a matter moving forward interacts with the antimatter produced moving backwards at the same time, it made me like more confident in this idea. But yeah, so to summarize, matter, you can think of it like the crest of a wave, like a wave front that's moving with the crest upwards, and antimatter like a wave front with a crest that's with a trough underneath. And then you're like, okay, but what about the mass? Like, if one's negative, are you saying it has a negative mass? No, it does not have a negative mass. No negative mass, apparently. What mass is in this idea is the curve that is created. You see that, like, this trough right here, this wave front just moving forward in that direction. That is a particle with positive mass. See this guy moving backwards? That's an antiparticle with negative mass. The mass is the actual curve experienced relative to normal space. And the reason why I think this is fair to assume is because of matter-antimatter annihilation. You can picture a trough and a crest kind of meeting and canceling each other out until it's zero energy again. And one interesting thing about matter and antimatter is when they do, meet up and explode, it's a very efficient explosion that like releases all its energy outwards, almost like it's flattening out the space, and all those ripples freely ripple outwards into other places, per se. But yeah, you can't just say per se, per se. It's a meme. So anyway, we have an idea of matter and antimatter as these troughs and these crests. Matter being a crest and a trough. And you can almost picture like a moment of flat space. And then someone dragged their finger through and then it just caused, boom, like that, right there. You see that? Backwards in time, forwards in time. Trough, crest. Okay. Now, that's one idea of thinking about it. And again, back to that idea of 180 and 360. So what am I really saying there with this like CPT reversal? So from the Big Bang, and we'll get more into that later, it's always been a weird question, like, why is there more matter in this world than antimatter? Like, if, everything was normal at the start of the Big Bang and we're in this high volatile state of volatility, where did all the antimatter go? And if we lived in this idea of a probability space, a higher dimensional probability space that we're moving quite literally through space-time to different worlds that we measure, but all the worlds are quite literally physically real at the same time. We just choose which ones we're able to quite like curve into and experience and measure and see by our motion through normal space. Like we are space-like objects, and when we move, we start to act more time-like, I guess, something like that. There's like space-like, time-like, and light-like. Space-like, you're moving much more below the speed of light. Time-like, I think you're moving. Light-like, you're moving at the speed of light. And then time-like, you're moving faster than the speed of light and going backward in time, or curving so fast that you're like, okay, so this really helps. You have the surfer, he's going forward, he's perfectly still. You have another surfer, he's moving slightly curved away, and you can see how time dilates for him like that, right? But then you have this idea of motion for these surfers. One that's just moving less than the speed of light, he's still space-like. He will still fall within a 90-degree cone of existence, or let's assume his universe is 90 degrees, right? A 90-degree cone of existence, right? But then if he moves fast enough, he's now moving light-like, meaning that he's like, if time wasn't growing forwards, he would just be doing laps around this unit circle right now. But instead, it's more like a spiral experience, because he's not actually like, time is always growing forwards for at least us when we move close to the speed of light or at the speed of light. And if we were to move faster than the speed of light, then he would be able to not curve outwards, but now possibly curve inwards in a light-like motion, in time-like motion. I don't know. Once again, not peer-reviewed, but think about the concepts for yourself, and would love to hear what you think in the comments below. Let's go. Cheap plug. Okay. So, yeah. You have this idea of multiverses that we're moving into and measuring and experiencing, and it's like, oh, what is possible in our universe? What could we possibly see in this universe? Would you ever see a pig fly in our universe? Well, as probabilities, as time goes on, the sector of a universe expands more and more, and the possible states we can measure, it grows with it. And you could think of it like, in a far future, human beings have invented technology that lets pigs fly. So if you stick around long enough, you will see pigs fly eventually, due to the law of large numbers and randomness and entropy. Cool. Pigs can fly. Okay. Back to antimatter and matter. So we have this idea of an imbalance where matter seems to be more in our universe. And that could be explained by the idea of starting from this Big Bang expansion state, an initial state, and then rippling outwards into the next possible state, to the next possible state, into the next possible state. And then as we do that, we're just measuring in our own 90-degree cone that happens to be the matter side. Or maybe we're antimatter and we just think we're matter. But yeah, so we popped out this way, and then there's an antimatter version where the universe is like, yo, why is there no matter in this universe, but there's tons of antimatter? And I'm assuming 90-degree light cones, because the math actually works very well with this. When you use the radius of TC without considering the Minkowski metric or special relativity, you'll see these diagrams that the particle goes when it moves, its motion quite literally goes beyond a 90-degree motion, and you will see the particle all the way to the left, or at 0 degrees after a certain amount of time. But when we use a radius of the Minkowski, it does this interesting stretching and squashing of space that shows that the particle's motion mainly stays within a 90-degree radius of space, or its own sector universe, right? And then you have this 45-degree chunk on the left, 45-degree chunk on the right, where sometimes the particle moves to that point. But we also see some very interesting interference patterns that happen when it gets really close to the edge like that, and we measure it all the way there at some time that's like, oh, did it travel super fast, or what happened there? Another interesting thing is, in most cases, for normal particles with no complex phase, it will look like the particle just froze at that point. There's no way the particle moved so fast that it got there. It's more likely that the particle was just perfectly stationary, and you just measured it in periodic moments at that specific point. So yeah, you can almost take any radius and then treat that as a existing universe. So in theory, it's 360 sectors of a universe that exists. And each one is just a straight line of time showing the evolution of events propagating outwards as a wave function or probability space. And we may live in the 0 to 180 sector and be able to experience at least a solid 90 degrees of possibilities. And hey, that's a good amount of degrees, especially when, time expands. Like, come on. So before I end on this section, I think one thing worth mentioning is this mathematical trick of transforming into spherical coordinates where the radius is relative to time or space-time is very interesting and helpful when it comes to mathematically formalizing the many worlds interpretation. A big issue with the many worlds interpretation is it leads to a lot of infinities. And if you're not familiar with it, it's basically the idea that it's like, oh, do I pick up this cup or do I not pick up this cup? There's a world where I picked up that cup, and there's a world where I didn't pick up that cup. So it splits into different sectors or different choices where I went left or I didn't go left. And in the world where I pick up the cup, do I drink from it or do I not drink from it? So that branch became more branches, and it continues to branch from every decision ever made. Ever. That's a lot of decisions to branch into, and it causes these infinities to pop up with no conservation of energy happening. Like, what the fuck, bro? Anyway, so yeah, the way this fixes this is by using the irrational number pi to consolidate those infinities. As the circumference grows, it still structurally handles the infinities growing outwardly. Back to this idea of the Big Bang and like a ripple outwards, because it does lend itself to the idea of a Big Bang, like this rippling outwards effect, as well as redshifting. I'm going to read through the notes first and then I'll do my random summary. All right, so then there's the Big Bang and redshift. In mainstream cosmology, the universe started as a super hot, dense state and has been expanding outwards ever since. If our circular radius started at 0 or time 0, that is our Big Bang moment. It's not an actual like specific moment in space and time, but an initial start state that's now rippling out to its next possible state from T0. And as it expands, any waves on the circumference stretch outwards, like how photons lose energy over cosmic time, so it stretches outwards and stretches outwards. The phenomenon we see as distant galaxies whose lights get shifted to longer wavelengths. So if you think of space and time as this continuous inflating circle, you see a natural cause of redshifting. The wavefront is literally getting bigger and bigger, and it's quite literally stretching further and further and causing this redshift to occur. If the universe does revolve around the idea of conservation of energy, you could picture this ripple, and as it expands outwards, like most ripples in water do, it kind of flattens out, and stretches outwards and outwards more. So it almost seems like it's growing and getting faster and faster away from each other in all directions. Yeah. Light cones and Planck steps. So we talked a bit about Planck steps and light cones, but let's do a proper dive into it. In special relativity, we talk about the idea of light cones and the idea that information can travel within a 40-degree region in standard diagrams, or plus minus 90 degree if you map angles a bit differently. And yeah, if you want that like nice circular spherical motion, but we can also think of it as 45 degrees. A big thing that tends myself to being interested in this idea of probability space in a radial line is that when you use the radial line to be the Minkowski metric, we see that conservation law in act, where the particle, a wave function that's purely quantum field theory with relativistic effects, follows the constraints expected of it, that the particle now is less likely to be found moving outside that 90 degree, 45 degree region of light cone. I thought that was very interesting. And especially if you add Planck steps, like discrete time steps where we know that, okay, in between those time steps, it's in a superposition of either this way or that way. It makes sense that, it was quite literally in a superposition of this way and that way, and then it moved outwards further into a new superposition of this way or that way. Let's say first tick, time 0. Now there's this moment of superposition where I don't pick up the cup, and then there's one where I do pick it up. Next tick, time 1. I'm now living in the world where I picked up the cup. Now a new tick happens, time 2. Did I drink from the cup or did I not? Well, in between that tick, I did and I didn't at the same time. Yeah, right, cool. We're living in that universe. So, yeah, it's a very interesting theory. It's visually understandable and comprehensible, which I really like, and I don't know if there's anything new to this idea other than like, yeah, the visualization aspect. I haven't seen something visualized this way before. So before we end off with just some cool experiments with these plots as well, I'm gonna do a quick nod to general relativity, because can't just confine to special relativity and how we're gonna do this for general relativity. I'm currently looking into this, but again, there's a lot more to this than just swapping out the radius, because you have to consider higher dimensions as well as full, like how would this map to curved geometry, and there's no direct observation yet that this visualization tool is testable for predictions yet, but I do hope it can lend itself to a way for viewing black holes and the quantum effects you see there. The reason why I think it may be possible is because we're able to not only use quantum field theory, but apply it in a comprehensible sense to special relativity and space-time motion. And yeah, it will be worth looking at how mass, antimatter, and many worlds, especially spinning black holes that could be seen as, I think there's a specific word for it, wormholes of sorts that due to their spin become invisible black holes or transparent black holes of sort that like almost lead to parallel universes of sorts on top of each other. And yeah, all right, in conclusion, this is the essence of time as a ripple through space concept. We touched on tons of ideas and literally just briefly yap my way through it all, but I hope you guys get the general idea. I'm going to add visualizations that could possibly make this more digestible. And yeah, what's next? Well, I plan to show actual plots from the simulations, which I've shown like the base ones, but I need to clean up the code more and like really start making this into a physics engine that I can play around with more, and would love to get feedback and get you guys' opinion on it. The code is open sourced and available. And yeah, make sure to subscribe and hit the notification bell as we post more about this topic and as the research expands further, or we find out it's all complete bullshit. We'll see. And yeah, thank you so much for tuning in for the very first episode of the Open Source Wizard. I'd love to hear your thoughts and questions. Please drop in the comments below. Let me know if I should keep exploring these mysteries and on the ripple of time. And yeah, until next time, happy exploring and stay curious. Yeah. All right, so before we end off, here are some interesting plots I got out. The double split experiment. Oh, I know, right? You can see how the probabilities, expand outwards in the circular motion. Scattering. Wow. I know, right? You can see how those probabilities expand outwards into different directions. It's nice. It's very nice. Complex phase of a Gaussian packet of sorts, wave function. Yeah, I know, right? You can see how the probabilities expand outwards in that circular motion right there. It's pretty nice, right? Yeah. Some other experiments I've done. Pre-claimer, most of these experiments were done using the Klein-Gordon. After I mainly finished working on the code for the Klein-Gordon experiment, and due to the added information from the Dirac, I need to do a couple more tweaks here and there to make it properly work. But yeah, I do have one base plot just to show the idea. All right, thank you. Yeah, I hope you could see how those probability plots expanded outwards in a spherical shape and showed different universe sectors on top of each other. Yeah, that's all. Thanks for watching. Peace out.